Today, we're going to dive into one of the most fundamental forces in the entire universe, electric charge. We're going to explore the simple rules that govern, well, everything, from a massive bolt of lightning to that sock that just won't stop clinging to your shirt.
So think about that for a second. What could possibly connect the incredible raw power of a lightning storm with something as simple as static cling? They seem worlds apart, right? But they're both driven by the exact same invisible force. And that force is electric charge. It's a property that's just as fundamental to an object as its mass. You can think of it as this hidden language that the universe uses, dictating how all these tiny particles attract, repel, and interact with each other. All right, so let's get right down to it. What exactly is this invisible force, and what are the basic rules it plays by? Well, the first thing to know is that it's actually beautifully simple. There are only two types of charge out there, positive and negative. That's it. And fun fact, it was actually Benjamin Franklin who came up with those names way back in the 18th century, long before we even knew about electrons or protons. And they just stuck. And the way they interact is just as simple. Like charges repel each other, so two positives will push each other away, and unlike charges attract. A positive and a negative will pull right toward each other. This simple little dance of pushing and pulling is the foundation for almost everything. From the bonds holding molecules together to, the reason that sock just won't let go of your pants. But where do these positive and negative charges actually come from? Well, for that, we need to zoom way, way in, down to the atomic scale. You see, every single atom is like a tiny balancing act. You've got positively charged protons in the middle, and then you have negatively charged electrons orbiting around them. Now, if the number of protons and electrons is exactly the same, the atom is neutral. But if it loses or gains an electron, that whole balance gets thrown off, and suddenly the object has a net charge. So how do you figure out the total charge of a bigger object? This is where a property called additivity comes in, and it's super straightforward. Since charge is what we call a scalar quantity, it just has a value, not a direction, we can literally just add them all up. The best way to think about it is like a bank account. Positive charges are credits, money coming in. Negative charges are debits, money going out. To find out your total balance, you just add them all together. It's really that easy. Okay, so charge doesn't just run wild and do whatever it wants. Turns out it has to follow some very strict, absolutely unbreakable rules. First up, the big one, the law of conservation of charge. Let's do a quick thought experiment. Imagine you've got a plastic rod and a piece of fur. Before you do anything, they're both electrically neutral. The total charge of this little system is 0. Now you rub them together, what happens? Some electrons literally jump from the fur over to the rod. So now the rod is negative, and the fur is left with an equal positive charge. But, and this is the crucial part, if you look at the whole system, the total charge is still 0. This proves a fundamental law of the universe. You can't create or destroy charge. You can only move it around. The next unbreakable rule is a bit of a mind-bender. It's called quantization. What it means is that charge isn't like water flowing from a tap. It comes in tiny, discrete, individual packets. And the smallest possible packet, the absolute fundamental unit of charge, is this incredibly tiny number right here, known as the elementary charge. This slide really makes it clear. You can have one of these packets of charge, or 2, or 3, or a billion, but you can never find half a packet or 2.7 packets. It just doesn't exist. It's just like money. You can have $1 or $2, but you can't have half a dollar in a single coin. Charge always, always comes in these neat little whole number packages. But wait a second. How could we possibly know this for sure? I mean, how do you measure something so ridiculously small? Well, the answer comes from one of the most elegant and important experiments in the entire history of physics. Let's travel back to 1912. An American physicist named Robert Millikan set up this incredible experiment. His goal wasn't just to measure the charge of an electron. He wanted to prove that this tiny, fundamental unit of charge even existed at all. The whole setup was just brilliant. He'd spray this superfine mist of oil droplets into a chamber. Then he'd peer through a microscope and watch a single tiny drop fall under gravity. But then, and here's the genius part, he would turn on an electric field, and he could make that droplet slow down, stop dead in midair, or even rise back up. By perfectly balancing gravity and the electric force, he could calculate the exact charge on that one tiny drop. And he did this over and over and over again. And here's the amazing punchline. When Millikan analyzed all his data, he discovered something incredible. The charge on every single oil drop was always a whole number multiple of one tiny fundamental value. He'd found it. He'd proven that charge is quantized, and in the process, he'd measured the charge of a single electron for the first time. So this brings us to our final and maybe our deepest question yet. What is charge, really? I mean, really think about this for a second. Is charge just an accessory that a particle carries around, like a little backpack? Or is it a fundamental part of what that particle is? To get our heads around this, let's compare charge to another property we know, mass. Now, you might not know this, but Einstein's theory of relativity tells us that an object's mass actually increases the faster it goes. It literally gets heavier as it approaches the speed of light. But charge, it's completely different. It's invariant. An electron has the exact same charge whether it's sitting still or zooming along at almost the speed of light. It never changes. And this is exactly what physicists mean when they say charge is an intrinsic property. For a particle like an electron, its charge isn't something it carries. It's part of its very identity. You can't separate an electron from its charge any more than you can separate it from its own existence. And this leaves us right at the edge of a profound mystery. We know that charge comes in these perfect little packets, but we still don't know why. Why does the universe do it this way? Why is it so perfectly, indivisibly quantized? And you know what? That's one of the biggest unanswered questions in physics today, and a pretty cool thought to leave you with.